Yeah, that clock keeps ticking till we start up in here. Yeah, that clock keeps ticking till we start up in here. If you came to learn chemistry, you did your part. Time is ticking down, so just be ready, cause it's about to start. When we solving for problems, we solve it information. You know Ben's Chem videos will provide you with equations. Never have to stop and think about it, this the station that will provide you with the chemistry all in relation. If you came to learn chemistry, you did your part.
Hello everyone and welcome to the Ben's Chem Videos Sunday night live stream. Tonight, we are going to discuss electrochemistry for the last time. That's right, you heard me correctly. This is the last of the electrochemistry live streams, and I think it's going to be a good one, just like last week and all the ones that came before it. So without further ado, I present to you Electrochemistry Volume 8. As always, your feedback is more than welcome and highly, highly encouraged, so please feel free to drop your thoughts in the chat, or better yet, you can call into the show via Discord using the link provided in the description. If you are watching live and if you are watching this as a video, please feel free to leave me a comment, because without your feedback, I am completely and totally lost. All right, so as we normally do, we're going to kick things off by reviewing the content from the previous live stream, which of course was Electrochemistry Volume 7. Volume 7 was all about batteries. So we all use them. We are all familiar with them. Battery is nothing more than a conveniently packaged voltaic cell. And of course, we should definitely know what a voltaic cell is by now, because we've been studying them over and over and over again over the course of the last several live streams. Got a message from Rohan Kumar, says, "Sup, Ben?" Hey, Rohan. How you doing, man? Thanks for coming into the stream. Hope you're doing well. All right, so we talked about batteries in Volume 7. I'm going to briefly review this. I'm not going to go into huge detail because that would take too long. I'm going to try to keep this brief. So I'm going to briefly touch on all the different types of batteries that we discussed in Volume 7. And if you would like to know more about that, then I highly suggest you check out Volume 7 or any of the previous volumes on electrochemistry. You can find them all conveniently located in a playlist called Electrochemistry Live Streams. Of course, there's a link down there in the description to that too. All right, so the first couple of batteries that we looked at are called dry cell batteries. Dry cell because they don't contain large amounts of liquid water. And the two that are shown on your screen are the common dry cell battery and the alkaline battery. And they're pretty similar in their design. In both cases, you have a zinc case that acts as your anode. That's where oxidation is occurring. It's the oxidation of zinc. And then in your cathode, you have a graphite rod, and it's the reduction of manganese dioxide that is occurring in your cathode. But of course, in the alkaline battery, the reactions are occurring under basic conditions. After all, that's what alkaline means. It means basic. And so if you look at your typical battery like this one, this is a D battery. And if you look very closely, it actually says alkaline battery somewhere here on the battery. I don't know if you can read that or not. So yeah, common dry cell battery, alkaline battery. The half reactions for those are pretty straightforward. But again, if you want to know them in more detail, I would suggest checking out Volume 7. Then we started talking about rechargeable batteries, beginning with the lead-acid storage battery. This is the battery that is found in most automobiles. So basically what your lead-acid storage battery is that 6 voltaic cells that are connected in series. Each voltaic cell contains a lead anode and a lead oxide cathode, right? And both your anode and your cathode are submerged in a solution of 30% sulfuric acid. And so what happens is the lead undergoes oxidation, the lead oxide undergoes reduction. The product of both of those reactions is lead sulfate, and if too much lead sulfate deposits on the surfaces of your anode and your cathode, then you will no longer get the flow of electrons, and the battery will die. But you can recharge this, you can supply electric current to this, to force the reaction in the reverse direction to regenerate the lead and the lead oxide from that lead sulfate. And that's how your lead acid storage battery works. Again, like I said, we're going to go through these briefly. So moving right along, we talked about a couple of other rechargeable batteries, the nickel cadmium or NiCad battery, and also the nickel metal hydride battery. And these batteries work fairly similarly. Over here in the nickel cadmium battery, you have a cadmium anode, so oxidation of cadmium. And then in your cathode, you have a substance called nickel oxide hydroxide that undergoes reduction. But of course, one of the problems with the NiCad battery is cadmium is fairly toxic, and so you have to deal with the disposal problems associated with that. The improvement over the NiCad battery is the nickel metal hydride battery. This battery is very, very common in hybrid electric vehicles. It has the same cathode reaction as the nickel cadmium battery, the reduction of nickel oxide hydroxide, but it has a different anode reaction. In the anode of a nickel metal hydride battery, you have a metal hydride, you have a metal alloy with hydrogen atoms embedded within it, and that is what undergoes oxidation in the anode of the NiMH battery. We also talked about the lithium-ion battery. The advantage of lithium-ion batteries is that lithium is the least dense metal in the periodic table, and so you can get a lot of energy out of it per unit mass. It has a large energy density, in other words. And in short, the way this works is you have these lithium ions that are embedded within graphite, and then that's your anode. Over in your cathode, you have a lithium metal oxide, like a lithium transition metal oxide. And when this battery is discharged, the lithium ions tend to migrate from the anode to your cathode. They migrate from your anode to your cathode, and the resulting migration of lithium ions causes a migration or a flow of electric charge. That's the simplified, dumbed down version of how the lithium ion battery works. Very, very useful, very prolific, rechargeable battery. And then the last battery that we talked about, and this is kind of important because this is going to kind of come back up again in tonight's live stream, is the fuel cell, right? So a fuel cell is basically a battery in which the reactants must be constantly replenished. And the most popular example of a fuel cell is the hydrogen-oxygen fuel cell, right? So you have hydrogen and you have oxygen both being pumped into this battery, into this cell, right? The hydrogen undergoes oxidation. The oxygen undergoes reduction. The only product of the reaction is water, right? So it's a very, very clean way to get some energy. But of course, the big limitation for this is the scarcity of hydrogen. The hydrogen must come from somewhere, and I think most hydrogen is produced by stripping hydrogen off of hydrocarbons, so this isn't exactly a super carbon neutral way to get energy. But that might change in the future as more efficient ways to produce hydrogen become developed. Who knows? All right, everyone. So that was the content from Volume 7. Like I said, it's a very, very good stream. I highly suggest you check it out if you haven't already done so. So let's get on to tonight's material. Tonight, we are going to be talking about a little thing called electrolysis. Electrolysis. So what is electrolysis? Well, electrolysis is basically when you use electricity to drive a chemical reaction that is otherwise non-spontaneous, right? So we've studied thermodynamics previously. We know that spontaneous means a reaction that occurs without ongoing outside intervention. Non-spontaneous reaction does need some sort of outside intervention to occur. And one of the possible ways that you can intervene is to supply electricity. So you supply electricity to drive a non-spontaneous reaction. So one really, really good example of this is the purification of metals, the extraction of metals from metal ores, right? So let's say you got like some iron ore. What that iron ore basically is it's the oxide of the metal. So it's like iron oxide or lead oxide. Most metals that exist in the Earth's crust exist as metal oxides, right? In order to purify that metal, you have to reduce the metal. The metal has to gain electrons, something that metals don't really like to do. Metals like to lose electrons. They don't like to gain electrons, right? So in other words, the reduction of a metal, which would be how you would purify a metal from a metal oxide, is a non-spontaneous process. But electrolysis can be used to force that reaction to occur to purify the metal. That's one example of electrolysis. Another example of electrolysis is the plating of metals. So like, let's say you want to plate something with silver or gold. You want to cover the surface of a more inexpensive metal with an expensive metal. You can use electrolysis to do that, right? You can use electrolysis. Basically what that means is you can have a solution of those metal ions, and you can force those metal ions to be reduced to the metal, covering it on the surface of the object that you want to be plated, right? So those are two examples of electrolysis. But one thing I'd like to do now is to sort of turn your attention back to that hydrogen-oxygen fuel cell reaction. And before I do that, let me actually go through this. This is a slide from all the way back to Electrochemistry Volume 2. So Volume 2 is where we first introduced the idea of electrochemical cells, right? We defined the terms voltaic cell and electrolytic cell. And for the past several streams after Volume 2, we've been talking about nothing but voltaic cells, right? So remember, a voltaic or galvanic cell, that's the type of electrochemical cell that produces electric current from a spontaneous oxidation reduction reaction. Tonight, we're going to be talking about electrolytic cells, which are electrochemical cells that consume electric current in order to drive a reaction that is non-spontaneous. So this is just kind of a refresher back from Volume 2, because we haven't really talked about electrolytic cells at all. So tonight is kind of our chance to do that. So let's go ahead and look back at that reaction that takes place in a fuel cell, right? So this is, again, what we talked about, among other things. This is what we talked about last week, right? So in a fuel cell, right, you have hydrogen and oxygen coming together to form water. It generates electric current. It's a spontaneous process, right? And so this reaction up here, it is spontaneous, it produces electric current, and it occurs in a voltaic cell. Specifically, it occurs in the hydrogen-oxygen fuel cell. What if we wanted that reaction to go the other way, right? So in other words, let's say I really, really want to get some hydrogen so I can provide hydrogen to fuel my fuel cell. How would I get that hydrogen, right? Well, one way that could potentially get you some hydrogen is the electrolysis of water, which is basically just the reverse of the reaction that takes place in the hydrogen-oxygen fuel cell. So instead of the water on the product side of the equation, you have water on the reactant side of the equation being broken down into hydrogen gas and oxygen gas. Well, since this is the reverse of a spontaneous reaction, it would therefore follow that the splitting up of water, the electrolysis of water, is a non-spontaneous process, and it consumes electric current. You must supply electricity to this system to force the reaction in this direction. And so it's non-spontaneous, it consumes electric current, and it occurs in an electrolytic cell. And so what would an electrolytic cell in which you have the electrolysis of water to produce hydrogen and oxygen gas, what would that look like? Well, here's a diagram of it on this slide here. So this is the type of electrolytic cell that you would use to get hydrogen gas and oxygen gas from water. Rohan says, is electrolysis interchangeable with electrolytic cell? It's the same thing. Yeah, exactly. Electrolysis is the process that occurs within an electrolytic cell. Again, it's using electricity to drive a non-spontaneous reaction, such as the splitting up of water into hydrogen gas and oxygen gas, right? And so this is the electrolytic cell that would be used to accomplish that, right? So notice that you have these two sort of tanks that are connected together by this common pipe, right? And this is basically just the solution that's in here. It's basically just an aqueous electrolyte solution, right? It is water that contains a soluble salt within it, right? And so if you connect a power source up to this and a couple of inert electrodes, right, what's going to happen is oxidation will occur at your anode, right? In this case, the anode is the production of oxygen, right? It's the oxidation of oxygen from water into oxygen gas. And then over in your cathode, you have the reduction of hydrogen in water to produce hydrogen gas. So in a cell like this, we don't really care as much about the oxygen because oxygen is fairly abundant. It's pretty abundant in the air that surrounds us, right? But the hydrogen, though, hydrogen is not so abundant. And so this is kind of a nifty way to sort of produce hydrogen from electrolysis, from an electrolytic cell, right? So one thing I want to sort of bring your attention to is something, and again, this is something that we've studied a long time ago, right? This is like something that we've not only studied a long time ago, but we've looked at it over and over and over again, right? This is the zinc and copper voltaic cell under standard conditions, right? So if you have zinc acting as your anode and copper acting as your cathode, submerged in a 1 molar solution of zinc ion and copper ion, respectively, then these are the half reactions that will sort of take place, right? And we also know, we can easily look this up in the table of standard electrode potentials to figure out what the cell potential would be under standard conditions of this type of voltaic cell. In this case, with zinc and copper, it turns out to be 1.10 volts, right? So this reaction occurs spontaneously, and it produces 1.10 volts of potential difference at standard conditions. What if we wanted to reverse the flow of electrons? What if we wanted the electrons to flow from the other way? Instead of flowing from the zinc to the copper, what if we wanted the electrons to flow from the copper to the zinc? Well, all we would have to do would be to connect. Let me move myself out of the way here for a second. I didn't really leave much room for myself. I'm just going to have to really minimize myself and take up a very, very small portion of the screen. There we go. All right. So if we wanted to reverse the flow of electrons, right, all we would have to do is to connect a voltage source. That's what this icon over here represents, is a voltage source that is greater than 1.10 volts, and that will swing it the other way, right? That will allow the electrons to flow instead of from the zinc to the copper, from the copper to the zinc. Now, notice that once we do that, once we connect that voltage source in place, the anode has become the cathode, and the cathode has become the anode. Remember, anode just means that's where oxidation is occurring, and cathode just means that's where reduction is occurring, right? Once you connect this voltage source in here, it changes everything, right? The copper becomes your anode because copper is the stuff that's undergoing oxidation. And on the flip side, you have zinc, that becomes your cathode because zinc is what's being reduced, right? Notice also that in a voltaic cell, we give a negative sign to the anode. The reason why we give a negative sign to the anode is because in a voltaic cell, the anode is the source of electrons, right? That's the source of that spontaneous flow of electric current. In an electrolytic cell, however, the source of electrons is not the anode. The source of electrons is the external power source, right? And what this external power source is doing is it's drawing electrons away from the copper. It's drawing electrons away from the anode. And so the anode in an electrolytic cell must be connected to the positive terminal of the battery, right? And by the same logic, the cathode, in this case zinc, is connected to the negative terminal of the battery because we're trying to drive electrons. We're trying to force electrons to the cathode where reduction is occurring, right? So you kind of, with electrolysis, you kind of have to think in terms of opposite, right? So once you connect that power source in there, anode becomes cathode, cathode becomes anode, and the flow of electrons completely changes direction. All right, so one thing that I wanted to talk about, now that we kind of understand electrolysis a little bit better, is the stoichiometry of electrolysis and how this can be used to solve a problem. So I'm going to take you guys to the whiteboard. Here we are. And we're going to learn a little bit more about the stoichiometry of electrolysis, right? So let's say I had a metal, like a ring, piece of jewelry, something like that, and I wanted to plate that metal. I wanted to coat that metal in a layer of gold. How would I do that? Well, one way we can do it, as you may have guessed, is by using electrolysis, right? So the reaction, or the half reaction that would occur in order to plate gold on the surface of a metal would be as follows, where we have gold, that's Au3+, the gold ion. You have an aqueous solution of gold ions, right, being reduced, right, gaining 3 electrons to produce just straight up gold, right? So in an electrolytic cell, right, since electrons, in this case for this half reaction, are on the left side of the equation, right, we can consider electrons to be like a reactant in this equation, right? And since electrons are a reactant in this equation, we can think of them as having a stoichiometric relationship with other reactants or products. Now, typically, right, if we're monitoring the progress of a reaction and we want to measure the amount of a reactant or a product, we can do that by measuring its mass, or maybe if it's a gas, we can measure its pressure, right? But with electrons are really, really tiny. So the most efficient way to measure how much electrons there are, or that have flowed through a cell, is by measuring charge, right? By measuring the charge in coulombs, because we know the charge of an electron, that is a constant, discovered by Robert Millikan way back in the day. And so that's the easiest way to measure the flow of electrons in an electrolytic cell, right? So we measure the total charge that has flowed through the cell, right? Now that total charge that flows through the cell depends on the electric current, right? Electric current, right, depends on the magnitude of it, but it also depends on the time, right? So remember, if we look at the SI unit for electric current, that is the ampere, right? Capital A. And 1 ampere of electric current is equal to 1 coulomb per second, right? So again, if we're trying to measure the total charge with the goal of measuring how many moles of electrons have flowed through an electrolytic cell, we need to consider not only the magnitude of the current, but also the amount of time in which that current has run through the cell, right? So what we can do is we can take the current, right, which is in coulombs per second, and we can multiply that by the time, which is in seconds, right? The seconds will cancel out, and that will leave us with charge, represented by the symbol capital C, right? Now, once we have the total charge, okay, we can use that along with the relationships that we've learned previously, right? We know the relationship between charge and moles of electrons. Those are related by Faraday's constant. So I'll do that in this purple color here. So Faraday's constant, right? Remember that one? Faraday's constant. This is something that's just good to commit to memory, right? That is 96,485 coulombs per mole of electrons. That's the total charge of 1 mole of electrons, right? So if you know what the electric current is, right, in amperes, and if you know the amount of time the electric current has run through, right, you can measure the charge, and then of course, knowing the charge, you can convert that into the number of moles of electrons. And then if you have moles of electrons, well, you can convert that into the mass of a reactant or product that was consumed or produced over the course of the reaction. And so what we're going to do is we're going to do a problem in which we apply these relationships with electrolysis to solve like a electroplating problem. So here we go. Let me erase all this stuff, and then I'll throw the problem up on the board, and then we will continue. We'll solve the problem. So, all right, let me see. Just a minute while I scramble to get this problem over on the whiteboard. How's everybody doing tonight? I hope you are doing magnificently well. Oh, I can't believe I didn't say it before, but happy Easter, everybody. Today's Easter Sunday, and I've had a good day. I've had a good weekend. You know, we went to church. We did an egg hunt. My daughters had a great time. It was overall a very, very good day. No complaints at all. Happy Easter, everybody. So, all right. So this problem tells us that we have gold, which is plated from a solution containing gold ions, according to the half reaction below. The same half reaction that we looked at previously, right? The reduction of gold ion into gold. And the question asks us what mass of gold will be plated by the flow of 4.7 amperes of current over the course of 30 minutes, right? 4.7 amperes for 30 minutes. So let's see if we can figure this out. Let's see if we can sort of reason our way through this, right? So again, we can get the charge, because again, that's how we measure the flow of electrons. We measure it according to charge instead of mass, right? Because electrons have a tiny mass. That would be very, very difficult, right? And so we can get the charge, I'll just say charge, right? By multiplying the current, which is 4.7 amperes. Now, of course, amperes is the same as coulombs per second, right? So I'll go ahead and change that to 4.7 coulombs per second, right? If we multiply that by the time, right, then we'll get the charge because the seconds will cancel out. But in order for seconds to cancel out, we have to take this 30 minutes up here and we have to convert that into seconds, which is pretty straightforward, right? If we have 30 minutes, right, how many seconds are in a minute? Well, that's pretty obvious. There are 60 seconds in a minute, so I'll put 60 seconds at the top of this conversion factor and 1 minute at the bottom of this conversion factor, right? So if we have 30 times 60, that looks like 1,800 seconds, right? I calculated that correctly. Make sure my units cancel. So 30 times 60, yeah, that's 1,800 seconds, right? So if I have my 4.7 coulombs per second, I multiply that by 1,800 seconds, right? The seconds will cancel out, and that will give me the total charge that has flowed through this cell, right? So, by the way, if anybody would like to follow along with their calculator, I've got mine right here. So, good to make sure we all sort of get the same thing. So, it's 4.7 times 1,800. And I got a value of 8,400, and let me put that 4 a little closer there, 8,460 coulombs, right? So we have 8,460 coulombs, which I'll go ahead and rewrite that down here. 8,460 coulombs, right? So now we basically just have to reason our way through this and convert our way to the mass of gold that is produced, right? So we're at coulombs. How can we convert coulombs into something that's going to be useful later? Well, again, as we saw earlier when I was sort of teaching on the whiteboard, we know the relationship between coulombs and moles of electrons, right? So if I put coulombs on the bottom of this conversion factor and moles of electrons at the top, we know that for every 1 mole of electrons, that's going to have a charge of 96,485 coulombs. That's Faraday's constant, right? And now that we have moles of electrons, right, we can use the balanced chemical equation over here for this half reaction to convert to moles of gold. And it looks to me like, again, if we set up this conversion factor to put moles of electrons on the bottom and moles of gold at the top, it looks like for every 3 moles of electrons, we have 1 mole of gold. Again, that's just from the coefficients of the balanced chemical equation from this reaction. There's a coefficient of 3 in front of the E minus, and there's an understood coefficient of 1 in front of the gold, right? And now that we have moles of gold, we can simply convert that to grams of gold using the molar mass of gold given from the periodic table. So this final conversion factor that I'm going to set up, I'll put moles of gold at the bottom, and I'll put grams of gold over here at the top. How many grams are in 1 mole of gold? Let me look at my periodic table real quick. Looks like it's 196.967. 196.967. That's how many grams of gold are in 1 mole of gold, right? And now I think that has pretty much solved it for us. As always, let's go ahead and make sure that our units cancel out. Coulombs cancels with coulombs. Looks like moles of electrons are going to cancel there. Looks like moles of gold are going to cancel there and there. And that looks like it's logical. That looks like it's correct to me, right? So at this point, all we have left to do is to punch this into our calculators, and this problem will be solved. So we have 8,460 divided by 96,485 divided by 3 times 196.967, 196.967. And I guess I'll keep this to 2 sig figs because 4.7 amperes was in 2 sig figs, which would be 5.8 grams of gold, right? 5.8 grams of gold. Let me go ahead and highlight that. So yeah, that's basically it. That is the mass of gold that would be plated by the flow of 4.7 amperes of current through this cell over a time period of 30 minutes. All right, everybody, that is going to do it for me tonight. I hope that this stream was valuable to you. I hope all of the streams within this electrochemistry live stream series have been valuable to you. I've had a lot of fun doing them. I hope you guys, like I said, I hope you guys have gotten something good out of them. More than happy to hear your feedback on what I should cover next. I recently announced that I'm going to cover organic chemistry pretty soon, and so I'm kind of faced with this decision on whether I should start covering organic chemistry next week to do that next, or should I cover some other general chemistry topic before I get into organic chemistry? I don't know. I'm kind of torn, which having some feedback from you guys on what I should cover next would really, really help me sort of figure it out and steer me in the right direction. I'm leaning towards starting to cover organic chemistry, but again, I'm happy to respond to whatever feedback you have. And all right, everybody, that's it. Again, I hope you've enjoyed this. If you want to watch any of the other live streams in this electrochemistry live stream series, look no further than the description where there is the playlist that has all these live streams in it. And all right, everybody, thank you very much for watching, and I will talk to you very soon. Take care.